Hello my friends, today I have the pleasure of sharing with you my favorite equation of all time, the Dirac equation. There is so much that can be said about the Dirac equation. There's so many different ways of formulating it and ways of looking at it and exploring it. There's so much structure in this equation and it has such far-reaching implications that you could read books upon books about it. So today I have a pretty modest and narrow goal. I just want to derive the Dirac equation so that you can see where the equation comes from. So let's put on our chef's hats and cook up an equation. First thing we have to know is what are the ingredients. So first things first, we're going to put in the mass shell. So the essence of the mass shell is that the form momentum of a particle dotted with itself always has magnitude mc quantity squared regardless of the inertial reference frame of the observer. So, form momentum is a 4-vector. And if you want to split that up in terms of energy and momentum relative to a given coordinate system, you can do that, and applying the Minkowski metric, we see that E over c squared minus the magnitude of the 3 momentum squared equals mc quantity squared. That is the equation that we're going to be working with for the mass shell. Okay, now next, ingredient number 2 in our equation is going to be the quantum energy and momentum operators. So this is that the form momentum is I times h bar times the 4 gradient of the wave function. And again, if you want to write that in terms of energy and 3 momentum, we get that the energy operator is I times h bar times partial derivative with respect to time, and the momentum operator is negative I times h bar times the gradient. Okay, now wait a minute, you might be thinking, hey, this is just Klein-Gordon all over again. I don't want Klein-Gordon, I want Dirac. I came here for the Dirac equation. So last but not least, ingredient number 3 is that the equation has to be first order in space and time. And that constraint is the cause of all of the wonderful, beautiful, mysterious structure and texture of the Dirac equation, as we're about to see. It's really, really hard to mix the third ingredient in with the first two and have everything work out. And when we do this, we're going to find that we have to encounter some pretty bizarre mathematical objects. Okay, so where do we go from here? How do we get these things to mesh together? Well, the first and second principle are pretty straightforward, because the mass shell gives us an equation where we have energy and momentum, and so all we have to do then is plug in the energy and momentum operators into that equation. Problem is, as long as the mass shell has energy and momentum squared, then those energy and momentum operators are going to be second order, so that's no good. Okay, well, what we want to do now is just combine the first and third principle so that we can write the mass shell in a way which doesn't have any squared energy terms or squared momentum terms, but rather just has energy and momentum appearing in the equation to the first power, because then when we put in the energy and momentum operators, we'll end up getting first derivatives. Okay, so given the mass shell equation, how do we rearrange it so that E and P just appear to the first power? So how do we do it? Well, first things first, why don't we try taking a square root of both sides? But the problem is, okay, you can put a square root sign over it, but how do you actually factor out that square root? Because it's not as simple as it looks. So here's what we're going to do. We're going to force that square root to be linear. And what I mean by that is we're just going to write out the form that we want it to take. So we know we want it to be linear, and so we can write out what we want to have. So on the left side of this equation, we have A times energy over speed of light, plus B times momentum in x, plus C times momentum in y, plus D times momentum in z. And now we're just going to say by fiat that that has to equal the square root of the form momentum dotted with itself, which is that expression under the square root with the squares of the energy and momentum. And now the question arises, what are A, B, C, and D? Well, let's go ahead and square both sides of this equation so that we have the quantity. Oh, and by the way, do you mind? I'm going to drop out the C factor for the speed of light. We'll put it back in later. I just don't want to carry it around. So this just makes the equation look a little simpler. Okay, so what happens when we square both sides? Well, first, let's look at the left-hand side of this equation. We have the AE plus BPX plus CPY plus DPZ quantity squared. And so when you square that whole thing, instead of 4 terms, you're actually going to get 16 terms, right? Distributive multiplication, like FOIL, but with more. And the best way to look at this, I think, is geometrically. So what I'm showing here is a square that represents that square, that represents that quantity squared. You can see along each of the sides, we have each of those terms listed out, so that the side length of the big square is AE plus BPX plus CPY plus DPZ, and then when we square it, we get that whole thing squared. But then you can also see the squares and the rectangles corresponding to those individual terms. Now before going further, I want to simplify this a little bit. So as it turns out, these numbers that we're looking for, these A, B, C, and D, they're a little bit weird, and they don't multiply the same way that things usually multiply. So we're going to be careful not to switch up the order that we're multiplying those. But the momentum and energy terms, these are just scalar quantities and they all commute with one another, and so we can go ahead and pull those out to the right-hand side of each expression. So what I'm showing here, the square on the right, it's exactly the same equation, but I'm just factoring out those energy and momentum terms and putting them on the right. Notice when we do that, there's the implicit assumption that those A, B, C, and D terms commute with energy and momentum. And it turns out they do, but just be aware that that's a little implicit assumption in there. Okay, so that is the left-hand side of that equation, and now let's go ahead and look at the right-hand side of the equation. So when we look at the right-hand side of the equation, we have energy squared minus the momentum component squared, and I'm representing that with a very similar kind of diagram as before, but this time it's just the diagonal terms. It's just the terms where the components are squared with themselves. And also, the other thing we have to keep in mind is that the energy square is positive, but the momentum squares are negative because of the Minkowski metric. Oh, and by the way, I'm letting these squares breathe because we have to solve this for all possible energy and momentum, and those things are variables. So we're not allowed to set them to be certain values and then do some kind of trick where the rectangle here adds up to a different rectangle. No, we have to solve it for a general energy and momentum. Okay, so how can these things possibly be equal? I mean, there's a number of problems here. First of all, clearly the off-diagonal terms have to go, because on the left side they're there and on the right side they're not there, so somehow they have to cancel each other out. But because this diagram is allowed to breathe, the only way we can ensure that those cancel out is if each off-diagonal cancels out with its own symmetric counterpart. So in this diagram, each of the off-diagonal rectangles has to cancel out with the other rectangle of its same color. Because otherwise, as the thing breathes, if you were to say, okay, two of these rectangles cancel out one of those, well, that's not going to hold in general, right? So they have to cancel out as pairs. At the same time, along the diagonal, how do we make those momentum terms negative when we have b squared, c squared, and d squared? That's a little weird, right? But maybe that's not so weird. Well, anyway, so after staring at this for a while, you can figure there's a certain set of constraints on a, b, c, and d that actually make these two things equal, and that must be true if these things are to be equal. And so the first thing, the most straightforward thing, is that a squared has to equal 1. Look at that white square, that energy square. On the left side we have a squared, e squared. On the right side we have e squared. So therefore a squared must be 1. Likewise, b squared, c squared, and d squared all have to be -1. Okay, we're familiar with the complex numbers, so the idea that we're squaring something and getting -1, that's not so unusual. And if that's all we had, we might say, oh, maybe that's something like the imaginary unit. But the plot thickens, because look, when you figure that the off-diagonals have to cancel each other out, look at those pink squares, AB and BA. Well, therefore, AB plus BA must equal 0. And likewise, AC plus CA, those light green squares, those have to cancel out too, so that also has to equal 0. And AD plus DA has to equal 0. And BC plus CB has to equal 0, and BD plus DB has to equal 0, and CD plus DC has to equal 0. And so look, we have this set of constraints, this set of 10 constraints on what A, B, C, and D have to be. And it's kind of confusing because you'll notice that, for example, take the equation AB plus BA equals 0, that means that A times B is not the same thing as B times A. So these numbers, A, B, C, and D, they're not going to be commuting with one another. In other words, the order matters, how you multiply A times B matters. And that right away tells us that A, B, C, and D cannot be real numbers, and they cannot be complex numbers, because both the real numbers and the complex numbers are commutative. AB equals BA, whether it's real or complex. And if we want to do something that doesn't commute, then we need something that's more exotic than just a real number or a complex number. Just to give you an intuitive example of how this kind of thing might be possible, consider the cross product. U cross v is actually negative v cross u by the right-hand rule. It's the same magnitude either way, but the directions are exactly opposite depending on the order that you take the cross product in. So the cross product gives us an example of how there's at least one kind of multiplication that can be non-commutative. And if we want to generalize that notion, we find a lot of flexibility in matrix algebra. So for the rest of the video, we will be looking at the solution that Dirac came up with for A, B, C, and D, where each of these is a 4x4 matrix. And it's important to know that this is not the only direction we could have gone in. There's actually very many different mathematical objects that obey these commutation relations, that is, that obey these constraints on what the products and the sum of the products have to be. The Dirac matrices are just one way of doing it, but they're sort of the most standard way of doing it. Alright, so here are the Dirac matrices. The Dirac matrices are also called the gamma matrices, so gamma 0, gamma 1, gamma 2, gamma 3. In spirit, the gamma matrices are just the A, B, C, and D that we were looking for. By the way, you do not have to memorize the Dirac matrices, okay? You can look them up. So now, if we return to the equation where we took the square root of the mass shell, and we substitute in the Dirac matrices for A, B, C, and D, what we end up with is an equation where each of the gamma matrices is multiplied by each of the components of the 4 momentum of the particle. And that equals the square root of the 4 momentum dotted with itself, right? Which equals mc quantity squared, and so you take the square root, you get mc. So effectively what we've done here is that we've taken the square root of the mass shell. So it turns out that there's a way of writing this equation in a really concise form. So notice that each of the Dirac matrices is multiplying by each of the components of the 4 momentum. So if we want, we can write it in a really cool shorthand where we just say gamma mu p mu. So what that means is the repeated indices mean we just sum over all of these indices. So mu goes from 0, 1, 2, and 3, and we add up these terms. So this is the Einstein summation convention, where if you get a repeated index, you add over all those terms. And so what we're looking at here is the Dirac equation in momentum space, where we see that when you take each of the Dirac matrices multiplied by each of the components of the 4 momentum, and you add it all up, that gives you the mass of the particle times the speed of light. That's a beautiful concept, and there's so much to say about it. We've got so much exploration to do in future videos. I'm really excited for all of that. But now, to go from momentum space to position space, let's go ahead and plug in our quantum mechanical energy momentum operator. So remember that second principle we started with when we were listing out our ingredients of the Dirac equation. It's that the 4 momentum is I times h bar times the 4 gradient. Well, we plug that into our momentum space Dirac equation, and we can keep it concise for now. We can use the summation convention. We'll unpack it in a moment, but just to keep things nice and clean, we end up getting that gamma mu times I times h bar times partial mu equals mc. So now let's go ahead and divide by I times h bar, and let's go ahead and move m over to the left side of that equation, and what we end up with is the Dirac equation. There it is. You'll often see this written with the I and the h bar on the left side and the gamma terms. It doesn't matter. So I know the Einstein summation convention can be a bit cryptic sometimes, but if we go ahead and unpack that and write that all out in terms of the derivatives, we can see that basically what we do is we're going to take the derivative of psi with respect to time, with respect to x, y, and z, and each one of those terms is going to be multiplied by the corresponding Dirac matrix, and then you're going to add in mc over h bar times the imaginary unit times psi, and all of that balances out so that equals 0. And if you look at this equation, it's like a flattened version of the Klein-Gordon equation. It's like we've taken the square root of the Klein-Gordon equation in some sense. So the fact that we were able to do that is going to resolve all of our concerns that arose from the Klein-Gordon equation relating to the second order in time. So that's great, we've done it, fantastic. But, well, here's the thing, but think about what this means for psi. So psi can't just be a complex valued wave function anymore because you have to be able to multiply it by a matrix, at least in this formulation of the Dirac equation. You know, we're using gamma matrices. So therefore psi has to be a 4-component vector, or a 4-component something, in order to do the matrix multiplication. Now, as it turns out, psi is what's called a bispinor. And believe me, we're going to unpack that in a future video, but long story short, there are these things called spinors, and a spinor is usually represented as 2 complex numbers. So psi in the context of the Dirac equation is a thing that involves 4 complex numbers at every point in space-time, but those 4 complex numbers really should be thought of as 2 spinors, where each spinor is a pair of complex numbers. For reasons that we'll see in future videos, when you write psi as a column vector like this, psi1, psi2, psi3, psi4, where each one of those is a complex number, then the first number, psi1, corresponds to a spin-up electron. The second number, psi2, corresponds to a spin-down electron. The third number, psi3, corresponds to spin-up positron, and then psi4 corresponds to spin-down positron. So contained within psi are 2 spinors, one for matter, one for antimatter, and each spinor has this spin-up, spin-down kind of component, kind of situation. Now, spinors are highly non-trivial objects. they're very difficult to imagine and visualize. So I think in the next video, I'm just going to look into different ways of visualizing spinors. Because, when you're dealing with a Dirac equation, it's a bispinor field. It's two coupled spinors at every point in spacetime. So in order to really work with this equation, we've got to become familiar with what a spinor is. So I'm going to go into that a little bit in more depth in the next video. And over time, as we practice with these equations, we'll start to develop a familiarity of it. But the weirdest thing about spinors, you can imagine it sort of like a flag. So, a vector points in a direction and has a magnitude, but there's no rotational sense around the axis of the vector. A spinor has direction and magnitude and also has kind of that orientation, the flag rotation angle, But when you represent spinors that way, there's actually two spinors for every imaginable flag. And when you rotate a spinor a full 360 back to itself, it becomes the opposite flag. And then you have to rotate it another 360 and then it becomes its original flag. So spinors give us a double cover of the rotations, and it's really cool, it's really trippy, and this is at the heart of why electrons are fermions and they spin one half, and it's really weird and there's beautiful structure here. So anyway, there's a lot more to talk about in the future videos. But for today, my goal was to derive the Dirac equation, and I hope that I have done a decent job of that. And yeah, so there you go. Thanks for watching, and I'll see you in the next one.